So, last time I gave you this axioms of vector space. I will not go into all that. I also told linear independence, dependence, span of a finite set of span by a finite set of vectors of a vector space. What is meant by subspace of a vector space, linear dependence, independence, utility of this independence, dependence, and all those things. Right? I have not given any example that I will do, and then I was in the midst of an exercise that I will continue again. That is, suppose you are given a vector space V, from which you pick up, again I tell you that this is my way of arriving at some concept of dimension without diluting any mathematics. Suppose you find out on alpha 1, and again mind you this alpha 1 could be anything. So, again there is plenty of choice, alpha 1 where alpha 1 is non-zero. This is not the zero vector of the vector space. Pick up an alpha 1 element of V. Then we define W 1 as the span of alpha 1. That means typical element of W 1 will be what? A constant times alpha 1. Span of a few elements means all possible linear combinations. Here only have only one element. So, all possible terms like C into alpha 1 for all C. Okay, W 1. Next to consider alpha 2 element of V and not element of W. That is from outside W, but from inside V. Because after all here you find W 1 is a subset of V. So, if W 1 is less than V that way in size, you go outside W 1, remain in V, pick up somebody from there and call it alpha 2. So, obviously, alpha 2 cannot be 0 vector, because alpha 2 is outside W 1, 0 is unique for the vector space. So, the 0 of V, the 0 of W 1 they are same, only one 0, and that is why this cannot be 0, because I am outside W 1. So, it cannot be 0. Then it means alpha 1 alpha 2 is Li, linearly independent. This I proved last time, again we can see, because if you form a summation like this, you get it to 0. Is it that only solution is C1 equal to 0, C2 equal to 0? That is a question. So, suppose it is not, suppose both C1 and C2 are non-zero. Obviously, you can write alpha 1 into alpha 2 in terms of alpha 1, some constant times alpha 1, which means alpha 2 is a part of W 1, which is contradiction. So, that is not possible. So, is it that one of them non-zero and other 0, will that be okay? So, this is 0, C1 alpha 1, say C1 non-zero, C2 0, suppose, is this fine? C1 non-zero, alpha 1 0, C1 non-zero, C1 alpha 1 0 means from our previous class we know in such case alpha 1 has to be 0, but alpha 1 was started with non-zero. So, that is not possible. On the other hand, is it that C1 non-zero, C1 0, C2 non-zero, then C2 times alpha 2 equal to 0 means alpha 2 has to be 0, which is a contradiction, that is not possible. So, only possibility is 0 0. If that be, then you consider W 2 as span of. So, then easily you can see W 1, after all you are considering all linear combination alpha 1 alpha 2. So, the combiner coefficient with alpha 2, if you hold that 0, then you get only constant multiple of alpha 1. So, that means all elements of W 1 are present in W 2, is not it? Suppose W 2 is still not V. You understand that from W 1 I am going to a bigger subspace which contains W 1, that subspace is W 2. If it is still not V, then again go outside W 2, from within V but outside W2, that is we pick up another guy, say alpha 3, this is W1, W2. If it is not in W2, it is not in W1, that means it is outside W2. We find out. Obviously, alpha 3 cannot be 0, like here I should say alpha 2 cannot be 0 vector. Alpha 3 cannot be 0 vector because W2 consists of 0. 0 is unique. There is same 0 of V. I am outside W2, so alpha 3 cannot be 0 vector. Again, append this. This is again Li. What is happening is whenever I go outside a space and take somebody from there, append this to the basis. Mind you, this is alpha 1, alpha 2 is the basis of W2 because it is spanning this and they are linearly independent, isn't it? Alpha 1, alpha 2 is the basis of W2, alpha 1 is the basis of W1. What is happening is, if you go outside the space, subspace, bring somebody from there, then my claim is that somebody and the previous basis, if you form a bigger set, that is a linearly independent set. That is what I am trying to say. This is the one line conclusion. You have been given a basis and you are finding the subspace, fine, span by that. They are linearly independent because basis. You go outside the space, bring somebody from outside, that and this basis forms a linearly independent set. From the simple reason that that fellow cannot be written as a linear combination of this basis, because that means that fellow could, the third fellow, new fellow could is part of W2, but that is not possible. More formally, if you want to see that del Li, you form an equation like this. I go up to this and then I can apply dot dot dot, because then logic will be very clear. I do not have to go for alpha, I mean W4, W5 and all that. From this we can conclude. Alpha 3 we picked up. Okay. Is it that all solutions are, some non-zero solution possible? Firstly, suppose C1, C2, C3 are non-zero. Then obviously alpha 3 can be written in terms of alpha 1, alpha 2 as a linear combination, which is a contradiction, not possible. That means all non-zero not possible. Then 2 non-zero. So suppose these 2 are non-zero. Since alpha 1, alpha 2 has been proved to be linearly independent already, they cannot be non-zero. So is these 2 means again alpha 3 in terms of alpha 2. Alpha 3 can be written in terms of alpha 2, or if these 2, alpha 3 can be written in terms of alpha 1. In either case, alpha 3 is part of W1 and therefore W2, or part of W2. That is not possible.
Sir, alpha 3 is not a span of alpha 1 or alpha 2.
Yes.
So
no.
That alpha 3 can be jointly expressed in terms of alpha 1, alpha 2.
No. That is, you did not understand anything. What I said W2 is a span of this means set of all possible linear combinations. You have forgotten. So you have to span of, it includes only multiples of alpha 1, multiples of alpha 2, but not only that. Like x axis, y axis, but any linear combination of x vector, y vector. So entire xy plane. And I am going in the third direction. That cannot be written in terms of some combination of xy vectors, isn't it? So you understand 2 also not possible, because these 2, then they have to be 0. They cannot be non-zero because Li. And these and any of the 2 not possible, because alpha 3 again becomes part of W2, not possible. So 2 not possible, and then 1. 1 means suppose this is only this is non-zero. That means alpha 3 is 0, which is not possible. I suppose this is not. Okay, either this or this, again that contradicts obviously. Alpha 1, alpha 2, none of them is 0. 1 at a time also is not possible, isn't it? So they are linearly independent. Only solution is 0. This way you can proceed, because whenever you add extra vector, that extra term, if the coefficient there is non-zero and some others are non-zero, that extra term will be linearly expressible in terms of race. That is not possible. If that term has 0 coefficient, others have to be 0, because others have to be already been proved to be linearly independent. Okay, rest follows easily. You understand that this way what I can do from W3. So I consider now W3 as a span of alpha 2, alpha 3, right? Now if W1 contained in W2 contained in W3, okay, contained V. Again I go out of W3, bring a alpha 4, that cannot be 0 vector, append that to this can be proved to be linearly independent the same way, form a linear combination, the C4 alpha 4, if C4 is non-zero and either other 3 coefficients or at least one of the three coefficients is non-zero, immediately alpha 4 will be written in terms of either alpha 1, alpha 2, alpha 3 or part of them, which is not possible, because then alpha 4 will be part of W 3, which is contradiction, because I am going out of alpha 3. Okay. If C 4 alpha 4, C 4 is 0, that means the other coefficients have to be 0, because they are Li, C 1, C 2, C 3, they have to be 0. Okay. So, this way. So, suppose this is an algorithm of constructing bigger and bigger subspaces within V. If it so happens that after a finite number of steps, I arrive at W n and then W n coincides with V, that is, there is nothing outside W n. That is, for n less than infinity, if I mean you are getting a sequence of subspace, isn't it? W 1, if it so happens W n you arrive and that is equivalent to V, then that means you have alpha 1, alpha 2 dot 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 alpha n, you have constructed one basis. Fine. But remember, there is no nothing unique, because alpha 1 I started with purely arbitrarily, there are infinite choices of alpha 1, just do not take the 0 1. Then again I formed a W 1, outside W 1 I went, I took any alpha 2, that term any, again alpha 1, alpha 2, okay, I found out the span W 2, outside I went, I took any alpha 3. So, this choice is not unique. The number n, however, so what it means is you could start with another say element beta 1, not 0, consider its span W 1 prime, go outside that, but inside V take another vector say beta 2, beta 1, beta 2 linearly independent, take its span called W 2 prime dot 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 dot, this way you go. So, you get another sequence of vector spaces, but total number will be same, the total number is n and that n is called dimension. Dimension does not depend on the choice of the basis, we will prove it. Have you understood what I said? That there is nothing unique about basis. Through examples it will be clear later. There is nothing unique about the basis. I can start at alpha 1, then alpha 2, alpha 3 purely, or I can start at some beta 1, find a space spanned by that, go outside that, pick up a beta 2. So, beta 1, beta 2, again this find the space spanned by that, go outside that, pick up another fellow beta 3. So, this way also you can get beta 1, beta 2, beta 3 and subspaces which are contained in nested subspaces, one contained in the other, that also contained in another. So, finally, also it will coincide with V after some finite number of steps, and my claim is that number of steps will be still same as n. That is, either it is alpha 1 to alpha n or beta 1 to beta n, or could be gamma 1 to gamma n, number is same and that number is called dimension. It is a magic number independent of the choice of basis. But basis does not have to be unique, as you can see. You can construct a basis in your way, in your own way, and there is infinite choice, right. So, this dimension thing we can prove easily. Suppose I start with beta 1 and beta 2 and all that. So, we go like this beta 1, beta 2 dot 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 dot, and suppose it I have got terms up to beta m, and m and n are not same. I will prove that m is equal to n. I will prove m and n are same, you understand, but in general I am starting with m. That means, this span also, span of this also V, suppose. Then I have to prove that m is nothing but n. That is what I have to prove. I started with beta 1, then got a beta 2, then got a beta 3. That process went on. Suppose after mth step, the corresponding subspace spanned by this coincides with V. That is, I stop there. Then my claim is that m will be nothing but our good old n. It cannot be a new number. I have to prove it. But one thing we know, this will be linearly independent by the construction. You take the space spanned by beta 1, take beta 1, go outside that space, find out any beta 2. So, beta 1, beta 2 linearly independent. Then take the space spanned by beta 1, beta 2, go outside that. Take a beta 3, beta 3, beta 1, beta 2, there, that proof, general proof we have done, isn't it? So, this is Li, there is no doubt about it. Only thing is m should be equal to n, that we have to prove, fine. That means, so suppose start with, we do not assume m equal to n. That means, either m is greater than n or m is less than n. We take the case m greater than n and prove that this is not possible. So, that means, m could be less than n. Then in the same proof, you reverse the role of n and m, and immediately you get that proof that m cannot be less than n also. You understood my logic? I will start with m greater than n, also it is not possible. So, you can ask the question, that means m should be less than n, but by the same proof, replacing interchanging the role of n and m, I will say that n also cannot be greater than n. So, only possibility that will appear is possible is m equal to n. It is not very difficult, it is an easy proof. Since beta 1, beta 2, they are all part of V, and V has another basis alpha 1 to alpha n, then each of these can be written as a unique linear combination of alpha 1 to alpha n. Any vector of V can be written as a linear combination of any basis vector. I am taking that to be the basis alpha 1 to alpha n. That means beta j, this notation I have to check a whether I j or j j I. Let me start with I j, alpha j. Why I? Because why j? Because I am taking, sorry, beta j, no? Yeah, because beta I, that particular vector is a linear combination of those alphas. So, j because of the corresponding basis vector alpha j, and I because starting vector is a beta I. So, I comes from here, j comes from here, okay, and j will be 1 to n, but these betas are linearly independent. So, if I form a summation C 1 beta 1 plus C 2 beta 2 plus dot 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 equal to 0, only solution should be C 1 to C n C m equal to 0, isn't it? So, suppose I form an equation like this, C I beta I equal to 1 to m, after all m elements, I am considering the case m greater than n. Suppose this is 0. So, since they are proved to be linearly independent, about that there is no doubt, whether it is betas or alphas, they are mutually linearly independent, that is true. From the way we have constructed them, we have already given that proof. Li is never in question, the number is in question, whether m and n will be same or not. Okay. So, since they are Li, only solution for this would be C 1 equal to C 2 equal to C m equal to 0, that we know. But suppose here I replace beta I by this expression and interchange the summation, because interchange the summation, what will you get? Actually, better would have been a j I here. Anyway, you will understand what I am trying to mean. So, this beta is replaced by this here, then the two summations are interchanged. So, j equal to 1 to n goes outside, and the I summation I equal to 1 to m a I j C I let me do one thing, just there is no, I mean, with this also is possible, but to get this in a nicer form, let this be beta j and this will be alpha I, C j beta j. Okay. So, beta j is given by an expression like this, beta j is a linear combination of alphas. I am just interchanging, I mean changing this indices actually. Beta j is given by a linear combination of alphas like this. These are the combiner coefficients. So, I, this will be a summation over I equal to 1 to n. Okay. A I j alpha I is coming from alpha and j is coming from j, that is better, fine. So, now I am linearly combining them equal to 0, they are proven to be linearly independent. So, only solution should be that C 1 equal to C 2 equal to equal to C m equal to 0. Okay. And you replace and interchange as two summations. So, that means I equal to 1 to n will be here, j equal to 1 to m, is that right? C j. What is the problem? This I am replacing here. This summation is here, then I am interchanging the two summations. Huh?
Left hand.
Here, here.
You're saying left hand index.
Okay, let me instead of correcting it, let me do it here again. One second.
That was right. Here.
Beta j.
So here
I am replacing this beta j. This one. This you can correct it. This. I didn't bother about this. I thought it is implied already. I was taking that in mind and proceeding. This is what you meant, right? Cj beta j, replace beta j by this, interchange the two summations. J equal to 1 to m, your Aij Cj, right, times alpha I equal to 0, but alphas also have been proven to be linearly independent. That means this is a linear, this is a scalar, remember this is a scalar, summation times summation of something times something, a scalar. So, scalar number depending on I is a function of some constant I, subscript I, that times alpha equal to 0. Alphas are linearly independent. That means each of these terms should be 0 for each I, isn't it? For each I this should be 0, but this term you can write as like this. Okay, you get this. But if m is greater than n, that means what? You have got more unknown less equation. So, obviously, I can find, I can say take some coefficient to be non-zero, and subject to that I can find a solution for that, so that is satisfied. It is a basic thing of algebra. Na? If you have more unknown and less equation, I can, all 0 is not the only solution. You can find a non-zero solutions easily, isn't it? But that is a contradiction, because what are the C's after all? Here they are linearly combining another linearly independent set, that is betas. There are two linearly independent sets, one is set of betas, set of alphas. They were combining the betas. The betas are also linearly independent. So, therefore, the only solution for this equation should have been that all coefficients are 0. But if you have m greater than n, you can always construct solutions for C1 to Cm where not all are 0, but still this is satisfied. So, there is a contradiction, isn't it? So, that is not possible. That means m has to be greater than either equal to n or less than n. If m is less than n, then I interchange the role of n and m. Interchange the role of n and m. I have just proved a property, m cannot be greater than n. Interchange the role of alpha and beta. Betas who are expressed in terms of alpha, you express alphas in terms of beta. Same thing, you go ahead. You understood this? So, only possibility is m equal to n, and in m equal to n you have a square matrix times this, and that is possible. The square matrix in that case will be invertible. An invertible matrix times a vector equal to 0 means the solution is 0. Okay. So, this shows that these two indices cannot be different, they have to be same, and that is called dimension of the space. We take some examples. Consider examples of vector spaces. 1. Consider just column vectors, say n cross 1 column vectors, A1 to say An, element of what is called Rn. You know this Rn means R is real number, R into R into R. Basically, all this means all the elements are from real. Okay. Now, set up all these, that is Rn actually, set up all this a vector space under usual notion of vector addition and all that, because if you take one vector another vector, if you add, you get a vector of the same dimension, isn't it? You get a vector of the same dimension, right? It does not become n plus 1. So, you remain in the same space. If you take one vector multiplied by a scalar, you still get another vector of the same dimension. So, you remain there. Then there is a 0 vector, means all zeros. That associativity, commutativity, they are they are valid very trivially. Two vectors are added means just terms wise they are added. Normal addition of column vectors. So, that is of course commutative, that associativity, all those things exist. there is a 0 vector. If you put all 0 here, that is the 0 vector in this vector space, because with that if you add any other column vector, you get back the same column vector. Then given any vector, you can find its so called negative, because you just reverse the sign. With that, if you add the original vector, you will get the 0 vector, so on and so forth. So, this is a vector space. Now, suppose in this vector space I consider set of all vectors whose sum, if you sum all the element, is equal to 10. So, those vectors will form a subset of this vector space, is not it? Because after all, I will consider only those vectors where if all the terms added will give rise to say 10. So, it will not be any vector from R n, but only selected vectors. So, that set will be a subset of this vector space, but is that a subspace also? You understood my question? Not understood. So, this is the R n. Now, I am considering vectors like this alpha, element of this R n is the space here, vector space, element of this, so that summation of alpha 1 plus alpha 2 plus dot dot plus alpha n equal to say 10. It could be any number 10. So, I collect only those vectors from R n, form a set, that is a subset of R n, subset fine, but is it also a subspace? Answer is no. You take one vector alpha 1 from that set, another alpha 2. In both the cases, if you add the two terms, you get 10. But when you add alpha 1 plus alpha 2 and then add the terms, you get 20. So, immediately you go outside the set, is not it? Or take a vector, all the terms added equal to 10, and now multiply the vector element by a scalar, immediately the sum of the elements after the multiplication will be different. So, you are not remaining in the set. So, that set is not, we say that set is not closed under addition, not closed under scalar multiplication, you go outside the set, and if it is not closed, it cannot be a subspace. Now, suppose instead of 10 I make it 0, I say I make it 0, that all the terms added equal to 0, then it will be a subspace, because you take any vector whose terms are 0 added 0, take another one, again terms added equal to 0. Now, if you add the two vector, resulting vector also, if you add the terms, you will get 0 only, or you take any vector like that, multiply by a scalar, and then resulting vector if you take and take all its terms and add, still it will be 0. The scalar will be common. Are you following me? Suppose take this and multiply by c, c into within bracket alpha 1 plus alpha 2 plus dot dot plus alpha n. Now, alpha 1 to alpha n if added equal to 0, after multiplying by c also is 0, is not it? So, that will be not only a subset, but that will be a subspace of R n. Okay. Consider matrices, say M cross, not M cross n, say square matrices to start with. This is we write actually R n cross n. No, actually this is how it is written, R n cross n. This set of matrices also is a vector space. Obviously, the same logic. Add two matrices of this size, you get the matrix of the same size. Take a matrix, multiply by the scalar, you get a matrix of the same size. All 0 elements, put 0 elements in all places, you get a 0 matrix. Reverse the sign of each element of a given matrix, you get the negative of the matrix. Those are trivially obtained. So, that is a space, vector space. There, if you consider say all matrices which are diagonal, then there is a subset of this, but it is not only a subset, it will be a subspace, because if you consider the set of all diagonal matrices, that set is a subset of this, I agree, because diagonal matrix of this size also is a matrix of size n cross n, is not it? A diagonal matrix of this size also is a matrix of this size, that is part of this vector space. But if you only pick up these diagonal matrices, form a subset, form a set, that is a subset of this, where only you are picking up a special kind of n cross n matrices. So, that is a subset, but my claim is that is not only a subset, that is also a subspace. because if you take one diagonal matrix, take another diagonal matrix, if you add them, it still remains a diagonal matrix only. If you take a diagonal matrix multiplied by a scalar, it still remains a diagonal matrix only, closed under scalar multiplication addition. Other properties follow easily. A diagonal matrix with all 0 diagonal entries is a 0 matrix. Diagonal entries you find, reverse the sign, it becomes a negative of the matrix. That is trivially done. Okay. Coming back to this first example, what is the dimension of the original vector space? But how do you come to that? Dimension of this column vectors, is n, capital N. How to show that? To show that, suppose I consider a set of basis vectors, trivial, we call it trivial basis. And then how many you can get? You can easily, suppose I consider E1, where I put 1 and zeros, then E2, and finally dot dot En. Okay. How many you can get such n? Are they firstly linearly independent? Answer is yes. Physically you can see any vector cannot be written as a linear combination of the rest, because where this guy is non-zero, that is equal to 1, others are all 0. Even if you combine the rest by some linear combiner coefficient and all, you cannot produce one out of the zeros with others. If you have to do it purely mathematically, multiply this by C1, multiply this by C2 and dot 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 and add, what will you get? C1 times C1 means only C1 here, zeros here. C2 times C2 means 0, C2, all zeros, so on and so forth. So, you get a vector where all elements will be C1, then C2, then C3 dot 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 Cn. Equate that to 0 means C1 equal to 0, C2 equal to 0, Cn equal to 0. So, linearly independent. So, fine, they are linearly independent. Then next question is, do they span the entire Rn? That means, if I pick up, they span a subspace, that is set of all possible linear combinations of this. Okay, that is a subspace spanned by them, a space spanned by them. They are linearly independent, is the basis of that space also. All that is fine. But is it that the space spanned by these fellows is nothing but Rn, is not subset of Rn, but it is the whole of Rn? Answer is yes, because if you give me any vector like this from Rn, I can simply write alpha as a linear combination, like alpha 1 times E1 plus alpha 2 times E2 plus dot dot alpha n times En, isn't it? That means they are not only linear independent, they also span the interspace Rn. So, that means they are a basis, they are one particular basis of Rn. Then from this I find out what is the number, capital N, but that is all I want. What is the number? How many basis elements? N. So, I know dimension of the space, that is N. Now, this basis you know, if you really expand alpha as a linear combination of this, what are the combiner coefficients you get? Alpha 1, alpha 2, do you get it in new information? No. Alpha 1, alpha 2, then alpha n, they are already available within the vector. But maybe you can form another set of basis vectors. Okay. How many? Total n. The moment I find another set of basis vectors and totaling capital N, another set of linearly independent vectors totaling capital N, obviously that will span Rn, where dimension of Rn is n. But maybe using them, if I try to express alpha as a linear combination, there will be new combiner coefficients C1, C2, maybe they carry some extra information which are useful to me. This is the basis of all transforms which you study. In the case of all, like I am writing as a vector, you just instead of vertical you make it horizontal, that will be a sequence of length n. DSP is all about sequences, 0th point to n minus 1th point, and this will become trivial sequence basis 1 0 0 0, that is delta n sequence, 0 1 0 0 0, that is delta n minus 1. So, this way you have n sequences, they form a trivial basis of the sequence space. Sequence space means sequence of all length, I mean space of all sequences of length capital N. I only want to know the dimension of the space. By this trivial basis I found out dimension is n, then forget about this basis. They give me nothing but the original samples of the given sequence alpha as their linear. So, I want to find out new basis, so that using that those basis vectors I can get new linear combiner coefficients to express current sequence. Understand? So, that is maybe I want to find out some new basis vectors, say gamma 1 to say gamma n, basis of say R n. another set of bases, but total number must be n, that is important. So, if you can find out linearly independent vectors, you cannot find more than capital N obviously, but if you find up to capital N which are they obviously span R n. What is the logic for that? Suppose they do not span R n, then you consider the span of this, that is contained in R n, because if gamma 1 to gamma n they are all contained in R n. So, their span also contained in R n. If the span is not full of R n, but contained in R n, that means outside the span, but within R n there is another vector, there is some space, from that I can pick up a vector append to this becomes a linearly independent set of n plus 1 elements, which is contradiction, because the vector space of dimension n cannot have more than n linearly independent vectors, is not it. So, you start constructing gamma 1, gamma 2 dot dot, and moment you arrive at n, you cannot get any more, but this gamma 1 to gamma n will be one basis. That way there is infinite choice of such bases. So, here I will pick up some basis, so that the linear combiner coefficient that is given any say alpha, I will write as C 1 gamma 1 plus C 2 gamma 2 plus dot dot. So, C 1 C 2 may give me some extra information, some useful information, not visible directly in alpha. So, depending on that, various basis vectors have been proposed. One is I will come to this little later again. One is DFT, another is DCT, another is Hart transform, another is Hadamard transform, so much and all this. Okay, I will consider this little bit more, little later actually. In some cases, the basis could be such that it so happens that when you try to find out linear combiner coefficient C 1, C 2, C 3 up to C n, you may find that only few are turning out to be big, sizable, others are very close to 0, because of the statistical properties of these vectors and all that. So, in that case I can achieve lot of compression, is not it? I do not need all the to store or transmit all the n, that is the basis of DCT. In DCT it so happens you have a compression in the coefficient domain. This coefficients, when you find out linear combiner coefficient, those are the transform coefficients, and when you write using the coefficients as a linear combination of the original vector, that is the inverse transform relation. Maybe little more I will consider after I cover inner product. So, you got these examples. I am not covering any further example. Now, because sequences are things of our primary importance. Similarly, instead of sequence, if you are dealing with continuous function 0 to capital T some period, take all functions within this, they form a vector space, because you add two functions, you get a function within the same duration only. Take a function multiply by a scalar, you get a function of the same duration only. A function that takes 0 value all along, this is the 0 vector, that is 0 function. You take any function, reverse the amplitude at any point, you get another function of the same size, same duration, that is the so called negative of the original function, so on and so forth. But they are, I will not go into that, is not algebra, they are actually the dimension is infinity. Dimension is infinity and the summation becomes integral, you get Fourier transform, analog Fourier transform, inverse transform results. That is more difficult study. In algebra, you do not have the problem. This algebra, all finite addition, summation, there is no integral, there is nothing continuity, discrete, this plus this or this plus this, okay, and finite dimension also. I am saying that that process will of finding a basis will converge after a finite number of terms, that I put cleverly. That is where everything is. After just finite number of terms, things converge. That means any vector will be a what? Linear combination of the basis vectors. But what kind of linear combination? Finite, and finite linear combinations are already defined in my definition, because in the vector space definition I give you definition of addition, vector addition, where you take only 2. So, 2 means if you have to add 10 vectors, 2 at a time, then another one, then another one, like that. This is possible as far as those axioms, but if I say infinite, there is no notion of infinite addition there. What is meant by infinite addition? How many times? You never know. That axioms give only addition of 2. It takes 2 vectors, give you another vector, not infinite vector. The infinity brings in all hell lot of trouble actually. But luckily for all our purpose, we are not dealing with those cases. Finite dimension of vector space, all accurate, no problem with that. Okay. Now, I come to another notion, that is of inner product, which is actually equivalent of your dot product. In the 3-dimensional another example was that 3D vector space or 2D vector, that position vector. Suppose this is a xy axis, you take this axis, any two vectors. The space that spanned by those two position vectors is interplane, because one vector another vector, if you linear combine, you get another vector. So, each point, if you draw a line from the origin, is a vector. So, this Space is nothing but a set of vectors starting from origin. Collection of all such possible points is this plane, and any vector or any point in this plane is a linear combination of the two directions you have chosen, and those two directions are linearly independent because one is not in the same direction of the other. So, one cannot be written as a linear combination of the or multiple of the rest. And then if you go to the upward direction, not necessarily vertically, even angularly upward, that new vector will be outside that space, because that is not in that space, and obviously that cannot be written as a linear combination of the previous two basis vectors or x's. Okay. So, these three will form a basis of this 3D world, but their dimension is 3. From the physical limitation only you can see you cannot go beyond. 3 means, but you can choose any set of vectors, not necessarily one of them is that vertical thing x, y, z, but it is not necessary that they have to be vertical. So, you can choose they have any arbitrary orientation theta, phi and those kind of angles, Still, as long as one is not in the plane spans by the other two, they are linearly independent, and by using them as a linear combination you can express any vector in the space. Okay. Dimension image 3. Choice of basis is infinite, either 3 vertical axes or 3 points at any angle with each other, making sure that one does not lie in the direction of another or in the plane spanned by the other two. Then the dependence will come up, so you cannot span the entire 3D world. Okay. Orthogonal is a special case when they are at 90 degree, but does it have to be 90 degree? See this. Consider the 2D plane. This is orthogonal. Obviously, these two are linearly independent, but suppose I do not take this, I take these two. They are not orthogonal, but still they are linearly independent. This is not something times this and vice versa. This is not the space spanned by this is this axis. Any point in this line is a scalar multiple of this vector. The space spanned by this vector is this line. I go outside this, so I bring any folly, not necessarily this guy which is at 90 degree, this fellow. This is obviously, if this and this are linearly independent, because this lies outside this place, this cannot be a multiple of this. Now, together these two will be spanning one space which is this 2D plane. You take any vector, you draw a line parallel to this and all, you can write any vector as a linear combination of these two, is not it? So, that means these two span the entire 2D plane. Then you go one step ahead, you go vertically up, not necessarily at 90 degree, but just point up by any vector. That vector again does not lie in this 2D plane. So, it is not a linear combination of these two. So, again consider the span of that new guy, this new guy and this previous two. They will span from our ordinary knowledge, they will span the entire 3D world. Any vector in this space can be written as a linear combination of those 3, which means this 3D world has a dimension 3. But basis is not unique. I could have taken east of this, I could have taken in this direction, this I could have taken in this direction, these two, third one I could have taken in another direction, but total is 3. Okay. Now, I go to that dot product thing, which is called inner product. There you are familiar with this notion something dot something, something dot something, but that dot will be gone, we will be using this notion alpha beta. Instead of alpha dot beta, alpha beta. I am not writing the full mathematical sentence that there is a finite dimensional vector space V and alpha beta are any two vectors. Just for all alpha beta element of V, this is the inner product called inner product, which is equivalent to a dot product, a more generalized notion of the dot product. In dot product, since it is a 3D world, specific vector space, there is a notion of length, there is a notion of angle and all that. You give a specific definition there, length of p times length of q times cos of theta, theta is the angle. But here in the abstract vector space there is no notion of angle. But people, mathematicians are so intelligent, they found out that angle and all they are not important actually, they give only the specific value, but there are certain basic properties that dot product satisfies there, which can be written in a very general way, and those properties are enough to get all beautiful layers that you get there also. The presence of cos theta only gives you a specific value of that dot product, exact value. Okay, but the properties do not depend on that, properties are more general. Okay. So, they found out and wrote some axioms that alpha and beta inner product, it is nothing but this means this is an element of the field C or R. Our vector space is defined over C or R. Mathematically, this means alpha beta, that is V cross V, inner product means V cross V mapped to C or R. You understand this, na? V cross V. Take one element from V, call it alpha, take another element of V, call beta. For any pair alpha beta, on every pair alpha beta, you define a scalar number. You map it to a scalar number, which is complex or real, depending on the field you have chosen. Okay. If you do not understand this, it means this inner product will give you a number, scalar number, which could be a complex number or real number, depending on whether you are dealing with complex field or real field. But then it should satisfy some basic properties, axioms. One is alpha 1 plus alpha 2 comma beta is separable. It is okay. These are axioms, this must be satisfied. If instead of one vector you write it as a summation of two vectors and then inner product is same as inner product is alpha 1, inner product is alpha 2, addition of the two scalar numbers. Then alpha beta is a complex conjugate of beta alpha. Alpha beta or beta alpha, one is the conjugate of the other. So, in the case of real field, there is no meaning of this, because conjugation has no meaning there. Then, if you take C alpha, C for any scalar, the C can be pulled out. That is, you take C alpha and the inner product is same as first do the inner product between alpha beta, multiply the scalar by C, you will get the same result. And last one is very important, all are important actually, that if you take the inner product of the vector with itself, like in the case of dot product P dot P, what does it give? Square of the length, that is more generally called norm square. It is denoted as this number, whether you are dealing with, irrespective of whether you are dealing with complex field or real field, that is inner product is in general a complex number or real number, this must be real. This is real and non-negative always, that is less than 0, less than equal to 0, sorry, greater than equal to 0, and equal to 0, that is greater than equal to 0, in that it will be equal to 0 if and only if alpha is the 0 vector. Okay. Remember this, alpha with itself will be denoted as norm square and it is greater than equal to 0 always, real non-negative, but it can be equal to 0 only if alpha is 0. Okay. Now, certain things we have to see. What happens if I
Second one is conjugation.
Yes. What happens if I take a 0 vector and with that I do any inner product? Out of these axioms it will follow easily. 0 means I can write 0 is equal to 0 plus 0, that is the definition of 0 with beta, and I apply this first axiom, it is again 0 comma beta plus 0 comma beta. Obviously 0 comma beta is 0, scalar 0. So, inner product with any 0 vector is 0. This says C alpha beta equal to this. If it is, if I generalize alpha and C beta, then it is, you can write C beta comma alpha conjugate from this relation. Then from this you pick up, that is conjugate of the entire thing, then take C out, then you again conjugate. So, you get C star alpha beta. So, C in the first coordinate or first thing, I call it a coordinate loosely, that can come out as it is, but C if present here it will come out with the conjugation. Okay. Now, if two vectors are such that their inner products is 0, they are called orthogonal. If two vectors are such that their inner product is 0, then they are called orthogonal. If on top of it their inner product, their individual norm is 1, then they are mutually orthogonal and their individual norm is 1, they are called orthonormal. Now, any vector can be normalized easily, forget about orthogonality. Suppose I give you vector alpha, its norm square is alpha square, which is this with itself, isn't it? I think we have just 5 more minutes. Alpha with itself. Now, suppose I define a vector which is nothing but, and alpha is non-zero, given to be alpha is non-zero. So, this is a positive real number. This is a positive real number, division by that is possible, no division by 0. This is a positive number, non-zero. Okay. In that case, if I from alpha I define a new vector which is alpha only, just a scalar multiplying, just a scaling of alpha. I will take alpha and use this square root of positive square root times alpha. So, it remains otherwise alpha, but just scaled, or you can write just norm of alpha times alpha, that I call alpha prime. This I am dividing by the norm of the original one. Okay. Then alpha prime will be unit norm. If you take alpha prime with itself, then what will you get? Put that here, put this thing here, alpha prime, put the same thing here. Then by the axiom 1 by norm alpha will go out, and from the second coordinate again 1 by norm alpha with the conjugate should go out, but this is a real number, isn't it? So, no conjugation. So, that means 1 by norm alpha square goes out, because it goes out twice from the first coordinate and second coordinate. What are left with alpha? There is alpha with alpha, which is norm square of alpha. So, they cancel and you get 1. So, very simple. You take the norm square, find the norm square of a vector, take the positive square root, call it norm, just divide the vector by the norm. Resulting vector is nothing but the original vector, just scale down. So, that your norm is 1. Now, if there are two vectors alpha and beta, they are mutually orthogonal, but each not having normal norm, unit norm, I can normalize alpha and beta by this factor, but orthogonality will prevail, is not it? Because after all alpha prime will be some scalar times alpha. That is, suppose alpha and beta 0, and I find that what I do, I make alpha by alpha prime, alpha norm, beta by beta norm. My claim is this also should be 0. You take 1 by alpha norm outside, 1 by beta norm outside, here you still have alpha comma beta. That is, in the space, suppose two vectors are at 90 degree. If you scale up those vectors, 90 degree does not change, they are even orthogonal. Same thing, na? I am scaling, so that this total thing has unit norm, total thing has unit norm. But are they, after this scaling also, are they even orthogonal, these total vectors? Yes. We take this constant outside, 1 by norm alpha, 1 by norm beta, that times inner product alpha comma beta, which is already given to be 0. So, that means they are even orthogonal, this is still 0. That means they are even orthogonal, you call this vector alpha prime, call this vector beta prime. So, alpha prime beta prime also are orthogonal, but with the added advantage that their norms are 1. So, unit norm, then they are called orthonormal, mutually orthogonal and each having unit norm, orthonormal. So, normalization is not a problem, you understand. Okay. Very quickly you see this result. Suppose you have been given some number alpha 2, alpha p in a vector space. P of course has to be less than or equal to dimension of the space, dimension of V. That we will see why. You are taking vectors and no alpha I is 0 vector, and given alpha I, alpha j is say delta I j. What does it mean? Quickly, because time is running out. This you will see why I am taking p little later. Alpha I non-zero means I am taking a set of vectors alpha 1 to alpha p, none of them is a 0 vector, and this is a orthonormal set. Alpha 1 is orthonormal with alpha 2, alpha 3, alpha p, that is why is the inner product. The moment I and j are different, 0, I and j are same, norm equal to 1, norm square that is equal to 1. But then you could say that if I just if I had alpha equal to 0, then at least orthogonality would have been present, isn't it? In fact, to prove this I do not need this orthogonality, I can have this, does not have to be orthogonal or normal. You can take some lambda I delta I minus j. What I am going to prove, it does not require normality, just orthogonality is enough. There is a set of vectors which are mutually orthogonal Okay, mutually orthogonal, that is only when I and j are same, it is lambda I inner product. Lambda is means norm, alpha with itself is norm. So, lambda is a real positive number, alpha I not equal to 0, because if you append 0, it is orthogonal to everybody, because 0 with inner product with anybody, 0 inner product with anybody is 0. Okay, so I am appending running out. Now, if I consider, I will say that this set is a linearly independent set. If they are mutually orthogonal, they are linearly independent, not the other way. Very easily you can say C 1 alpha 1 plus C 2 alpha 2 plus dot dot C p alpha p, if you equal to 0, is it that only solution is C 1 equal to C 2 equal to C p equal to 0? To see this, suppose I want to find out C k, is C k equal to 0? So, what I do, suppose I take the inner product of this entire quantity with say alpha k, then here also inner product with alpha k, but I have already proved the inner product of any vector with 0 vector is scalar 0, and in this summation you apply that axiom, you can separate out that inner product of C 1 alpha 1 with alpha k, C 1 goes outside, alpha 1 with alpha k, orthogonality 0, C 2 alpha 2, C 2 goes out, alpha 2 with alpha k, orthogonality 0. So, which term only survives? Only when C k alpha k, C k goes out, alpha k with itself, alpha k with itself is lambda k, and since I am not having 0 vector here, lambda k cannot be 0, norm square is not 0, lambda k is a positive number, strictly positive number. So, you get C k lambda k equal to scalar 0, lambda k is real greater than 0, that means C k equal to 0. Okay. So, a set of non-zero vectors, and the set does not contain of, when the set does not consist of 0 vector, a set of non-zero vectors and not consisting of 0 vector is a linearly independent vector. You understand then why I took P to be less than because in a dimension, in a vector space V of finite dimension, you cannot have a set of linearly independent vectors where number is greater than equal to greater than dimension. That is why, to be on the safe side, I took this. Okay, this is a very vital result. All the transforms that you study, they are basically orthogonal vectors with respect to some inner product. I will take that example. With some inner product, they are orthogonal vectors. That is all for today. Thank you.